This is Atulya, and this is part of my final assignment for the Coursera Machine Learning Foundation for Product Management uh, final assignment. So the problem that we are looking at here is to predict the electrical energy output of a combined cycle power plant using the four features that are provided to us. And the features that they've given us are temperature, ambient pressure, relative humidity, exhaust vacuum, which are collected on an hourly basis that will be used to predict the electricity output. So for the exploratory data analysis as well as the modeling part, I have used Python and specifically a tool called Jupyter Notebooks on Python for this analysis. So we will start off with uploading the data, checking for nulls, outliers, and if any of those are present, we'll treat them. Next, we will look at correlation between uh, the different features and power output as well as between the features themselves to select and settle on a modeling approach. So this is the Jupyter Notebook environment that we will be using to build our model. So the first step is to sort of import in all the libraries that are needed for this project. Next, we start off with uploading the file uh, that was provided to us by Coursera for this project and checking if all the values are present or not and if all the fields are there. Next, uh, as I mentioned, I'm looking at outliers. So essentially, what I'm doing here is I'm looking at mean, median, and min and max values for all the features that are present here as well as their percentiles. So if there were any outliers like really huge values or negative values which should not be there in the dataset as per the problem statement, we could take a look at those and exclude them or remove them with mean or apply other sorts of treatments if required. But as we can see from the output here, all the values lie between the ranges that are prescribed to us in the problem. So outlier treatment is not necessary here. Next, we look for nulls. These are essentially rows where an observation is missing. And what we can see here is that there are no nulls in the dataset. So the values are present uh, as per the problem statement. So there are no nulls, no outliers, so no treatment required for those. So next, we look at correlation between the different features and power output. So here what you can see from the correlation metrics is that power output has an extremely high negative correlation with ambient temperature and exhaust vacuum, whereas there is positive correlation, uh, slightly positive correlation between ambient pressure and relative humidity, though not as strong as the first two. And if we were to do a plot between power output and ambient temperature, exhaust vacuum, ambient pressure, and relative humidity, what we see in the first case is like a perfect linear correlation and a relation, and you can see it's just fitting the line. There is some deviation, but the data is mostly linear. For the next one, when we look at exhaust vacuum, the relationship is definitely linear, but the spread is slightly higher. And yeah, for the next one, the relationship is again linear, but there's a very high spread. So probably just using ambient pressure to predict energy output will not give us very high accuracy. And it's even worse for relative humidity because you can see that there's obviously some positive relationship here between relative humidity and power output, but there's like a huge spread here. So the relationship is not perfectly linear, and on its own, it means that it will not probably be a very good predictor of power output. So uh, based on this, correlations that we just now saw, I have selected linear regression as the approach to model power output. And for this, we will be splitting the data set into test and training data sets in the ratio of 10 is to 90, where 90% of the observations will go to the training data set, and that will be used to predict uh, power output. And then uh, we will try creating linear models with the combination of these four features to see where we can get the highest accuracy, and let's see if we can interpret it as well. So next, uh, we divide the data into training and testing dataset, and as you can see, the training dataset has 8,611 observations, which is 90% of the dataset, and the remaining 957 observations go into the testing dataset. So here I'm creating four different models. So the first model starts off with just trying to predict power output with temperature, and then we add exhaust vacuum to the second model, and then we add uh, ambient pressure to the third model, and then all four uh, to predict the power output in the fourth model. So once we've created these models, we look at the adjusted R square of these models, which is essentially the percentage of variation in power output that can be explained by the given model. So as you can see, model 1 can explain 89% of variation in power output using just ambient temperature. Uh, the second model, which uses temperature and exhaust vacuum, the accuracy goes up higher to 91.5%. Whereas the third model, uh, which is using all four of these features, has the highest accuracy, which is 92.8, almost 3%. So it essentially means that in the test dataset, the linear model is able to explain 92.8 or 93% of variation in power output using these four features. So next, what we do is we try to so this is based on the training data set, right? So we had that 10% of the observations saved away for our testing data set. So next step is essentially to use these different models and look at their accuracy on the test data set, so so as to see how it performs in the real world or in data sets or in observations which are not part of the training. So here you can see we are looking at mean squared error, which is the square of difference between predicted and actual values in the test data set when these models are applied on the testing data set, which is those 10% of observations that were left over. So as you can see, the first model has 5.29 as mean squared error, and the error percentage slightly decreases for the model 2, which uses exhaust vacuum, and remains more or less the same for the third one with ambient pressure, but seems to go down quite a bit for the one where we take all four of them, which is relative humidity, temperature, vacuum, and ambient pressure. So we can also plot it out here uh, to see the errors of the different models. And as you can see, all of them are linearly distributed, the errors. So there is no trend or anything else that we are missing it out here. So linear model seems to be the right way to go about it, because we don't see any patterns in the error and they are split on both ways of the lines. Between the different models, there is not much difference. But if you were to compare model 1 and model 4, where the sum of squared errors is zero point 0.5 lower in the final model, which uses all four features, you can see that the spread of errors is a lot lower as compared to the first model. So that's why model 4 seems to be the right model to go with us, since it has the lowest error in test population. So if you look at model 4, this is basically the summary statistics for model 4 that was on the training data set. So as you can see, it can explain 92.8% of variation in power output using these four features. And this is basically what the equation looks like. So, so here we can take a look at the relationship. So the linear equation looks like power output equal to coefficient, which is 459 or 460, minus 1.98 into temperature, minus 0.23 uh, into exhaust vacuum, and 0.06 into ambient pressure, and minus 0.16 into relative humidity. So we can see the same output here as well as a snapshot of the previous output here. So if we look at the p-value of all these variables as well as the coefficient, they are all below 0.05. So all of these are statistically significant, as well as the model's F statistic, which is also 0, which is lower than 0.05, which says that the model itself is statistically significant in predicting our output. So which is why I think this is the right model to go with it. And since we are able to get such a high accuracy on with linear regression, and we did not see any patterns in the uh, error terms, uh, it seems that this is the right model to go uh, with for this particular problem. We could have also used other approaches like decision tree, but then because the data is already linearly distributed, there is a chance that we might end up overtraining the trees, right? So that's why this approach seems to be correct. And